BN.
Okay, I'm in the middle of watching the third lecture. I think this is where I stopped watching his course. So I want to complete this course. So let's continue.
CNBN. And leave out the summation sign.
So this is just Einstein's convention how to do summation. Sum over n, bn, cn is just cnbn.
The only thing we have to be careful about, oh, incidentally, it doesn't matter whether we use n there. N is a summation variable. It's called a dummy index. It's not 1, it's not 2, it's just sum over 1, 2, 3, and 4. We could call it, if we like, exactly the same thing, sum over r.
Not now, later, but I can watch. Okay, let's watch it together.
Or sum over.
I got stuck here. It's really confusing. I wasn't able to follow. Let's try this time again.
M.
I mean, it should be straightforward. How difficult can this be? It's just conventions and yeah. I got confused with partial and full differentials. Like I'm not sure. I watched a bunch of lectures about a full differential and a partial differential mixed together. I don't have a problem with each one separately, but when you mix them, I'm confused. Like, I mean, isn't dx prime, isn't that the same as this dx prime? What's the difference? So my intuition is it's different ratios. It's just different ratios. So this is the slope, but this is not necessarily so. The dx is not necessarily the same size as the partial dx. Partial dx could be just no one guarantees that they're the same, even though they're both infinitesimal. They both tend towards zero, but there is a ratio between defy. I think it's this defy, the full defy dx, and the partial defy dx. Anyway,
when you're summing over an index,
he's just discussing the convention, the summation, Einstein summation convention. It's just a convention.
It's just
You just remove the sigma.
Notation that says
it's a notation.
Matter what you actually call it. All right, you just mustn't call it something which appears somewhere else in the equation.
He always says everything in plural. I don't know why he does that, but that's the way he talks. Somewheres else. That's the way he always talks. It's like New York talk or something. I don't know where he got it from.
Give it a name, the summation.
At this age, I don't think he can get rid of it.
Index, but make sure that it isn't the name that appears someplace else in the equation, because then you get confused.
I think he's talking about the dummy variable.
Okay.
The summation dummy variable.
So that's the summation convention. And the summation convention and the differential change in a field when you move from one point to another. Now, there's another rule. This is the second rule, which we will use over and over. And this is about all we'll use over and over. The second rule, and it has to do with change of coordinates. Change of coordinates, in particular, going from one set of curvilinear coordinates to another, but that doesn't matter right.
What is a curvilinear? I don't know.
Right now, we have a set of coordinates, which I've called x. But now let's suppose I use another set of coordinates that I call y.
So the set of coordinates x is x1, or I think x0, x1, x2, x3, and now he's going to have y0, y1, 2, and 3.
And the y's are different coordinates, so we have
completely different coordinates, nothing to do with the x.
Have some coordinate chart. There's our coordinate chart, or our coordinate map, if you like. But now I'm going to introduce other coordinates.
Okay, so this is the original coordinate system. It's x1, 2, 3, and 4. and there is a function, maybe it's a field function, I don't remember, it's been a month already, phi at x, where x is a vector. So um, so maybe this is x, and there is some value of phi at x.
That's, and these other coordinates could be strange curved ones if I like, or not. There's another set of coordinates, and I'm going to call those y. And the rule, of course, is that if you know what x is, if you know the collection of x's at a point, that determines a point, then there's a definite rule about what the values of y's are. That's what a coordinate transformation is. A rule for going from one set of coordinates, x1 through xn, for a particular point, to another set of coordinates. And so that means that the y's, they also go from, there are also a collection of them, y sub, let's call it n again, y sub n is some function. Let's just call it y sub n of all of the x's. Another
Confusing that he's using y sub n as the function, as this is the transformation function.
In other words, if you know all the x's, I can tell you what all of the y's are. If I want y1, some particular function of the x's, which is y1. If I want y2, likewise, and so on. And this, of course, is called a coordinate transformation. Yeah.
So getting back to the original equation for the infinitesimal movements, yeah. Do you know what kind of assumptions are being baked in about non-commutation?
So this is an infinitesimal movement. I think the movement is d phi. That's the movement. It's composed of dx1 and dx2. So you move in the direction of dx1, and the slope is d phi dx1. And you move in the direction of dx2, and the slope is d phi dx2. D phi is the height. So given a change dx1, dx2, and so on, and given a, like this is the function value. It has a value. So in terms of dx1, dx2, so you can think of it as x and y, and phi is z, or z is the height. It's the height. Let's say it's a terrain. It's a mount. I always think of it as a mountain terrain. So think of a mountain terrain. So I'm somewhere on the mountain terrain. Phi is the mountain terrain, and we have only dx1, dx2. We have x1, x2. That's the x and y, and phi is the height. So I'm wondering, if I move a little bit of dx1, a little bit of dx2, how much d phi did I move? So dx1, when you move in the direction of dx1, you multiply by d phi dx1, and that gives you how much you have gone up or down in the direction of x1. You do the same for x2, right? This is linear superposition. This is linear addition. So in the two directions have nothing to do with each other. So you go in the direction of x1, and you either go up or down, whatever the slope is, in the direction of x1. And you add to that, moving in the direction, a little bit in the direction of x2, you multiply that by the slope of phi in the direction of x2. So let's say you've risen 1 meter because of this, but you dropped half a meter in this direction. So you've gone up half a meter, let's say. So you went up 1 meter because of x1 direction, but you've gone down half a meter because of x2 direction, slope dropping. So together, it's 1 meter minus half a meter, it's half a meter. So let's say you've gone up half a meter. That is d phi. That's the definition of d phi. So the definition of d phi is moving in the positive direction of x prime a little bit, and moving in the direction of x2 a little bit. and you add basically the little bit of motion and the slope, a little bit of motion and the slope, and you get the total derivative. This is the definition of a total derivative. And during the lecture, he was asked, what is the name of this? And he didn't know that it has a name. And I went and I watched a bunch of lectures about the total derivative. And it's actually, it's a very confusing topic. Let's see, the timestamp is 29:30. Has anyone brought, I think people brought up the timestamp that it's a total derivative. Not this. Somebody, at least one person brought it up. There it is, total differential. Okay. And he didn't know. I think now he's being asked and he's not going to know, which is very surprising because even I know this and I barely know anything. I used to know a lot, significantly more, but I'm very old now.
Relations or infinitesimal movements as with respect to quantum mechanics when we do that?
Let's not get into quantum mechanics now.
Why is he asking about quantum mechanics? That is, what is he? What is that guy doing? We're just talking about coordinates, and that guy is like quantum mechanics. What are you talking about? This is just math.
Now, that's a.
Oh my God! If I were Lenny Susskind, I would be like, what are you doing? What are you trying to do?
Yeah, separate issue.
Separate.
You're going to ask me about second order quantities.
Well, I was kind of.
Right. That's what I'm thinking about. I'm thinking about the second orders. Like when you move to dx, and then you move, sorry, dx1, and then you move in the direction of dx2, then you're not starting from the same place, right? dx1, moving a little bit in the direction of dx1 and a little bit of dx2, this is from the original x1, x2. But by the time you moved from from the original x1 to dx1, this movement, there's no such place. But right, dx2 is from x2, but you're not at x2. You've moved. I mean, yeah, it's not so clear, but fine, whatever.
That was the other part of it, but
Yeah,
everyone in this class is very smart. They wouldn't be here otherwise. I think they were paying. This is from 1,000 years ago. Yeah, it's 1,000 years ago.
we're assuming all numbers commute, all expressions commute. Okay, for sure. As far as second order,
I don't even know what he means. What is commute? Commute to work? What do you mean commute?
quantities, this equation is first order in small quantities. All right, and that's what the D means as opposed to delta. Delta would.
What do you mean D? Oh, delta just means an actual numerical evaluation.
Mean an actual finite difference. And then, of course, it would be more complicated with higher orders and delta.
Yeah, nobody wants to do delta. Why would you want to do delta? What's the point of that?
Yeah.
is there some restrictions on what a coordinate system?
Like delta is when you do actual numerical analysis. You could do that, but we're doing actual math instead.
So that it's actually one value.
Yeah, absolutely. Every point has a unique.
Wait, is my streaming okay? I never tested my streaming. Let me check my stream on my YouTube's. Oh my god. Okay, let's watch my channel. La 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 la. La 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 la. Yeah, my stream seems to be surviving. Plus. Let's continue.
Set of coordinates and every.
Maybe I should change the title. So we're watching. Let me copy paste the title. This is the title. So we're watching. Colon paste. Okay, so maybe people will visit us and they'll join us. Let's go.
Every point has a unique set of x1s and x through xn's, likewise with the y's, and every set of x's, if I give you an x1 through an xn, that uniquely picks out a point.
But why is my quality so low? Quality? Really? There's only 240? That's it? My God, they recorded with minimal quality. Unbelievable. Let me see. Yeah, this is Stanford. This is the original production. Wow. Yeah, 1,000 years ago, people did not want to upload high quality. Wait, why? Okay, let's go.
A point in the space, let's call it P. And likewise, if I give you a point, that uniquely gives me a set of coordinates. That's the assumption
Either X or Y's.
of a coordinate frame. And the same should be true for the y's. So that means that there should be a one-to-one correspondence between x's and y's. Was that the question? Oh, for sure. Yes, we're certainly going to assume continuity, differentiability, and smoothness of everything.
Wow.
That's
just reality.
We're going to assume everything is as smooth as you ever need it to be, so that you can differentiate again, and never run into anything singular. So yes, that's another aspect. The x's and the y's are smoothly related to each other, as smooth as we ever need, depending on the circumstances. So that means continuous, differentiable, maybe even differentiable twice, and so forth. Okay, now here's the question. Supposing I know the derivative of phi with respect to all of the x's, xm for all the m's. In other words, I know this
for each one. So let's assume we know the partial differential of phi with respect to any single direction.
Set of partial derivatives of phi at a point. We pick a particular point, and supposing I know...
Thank you, cameraman, for not showing me where he's pointing. Good job.
At that point, how phi varies with respect to x's. I want to ask how it varies with respect to y. I would like to compute
the partial derivative from phi with respect to the x to the partial derivative of phi with respect to the y. That's nice.
Derivative of phi with respect to y sub n. And I'm going to write down the answer. If you don't know this, I ask you, please look this up. This is a tool that we will use over and over and over again.
Let's see if we can figure it out intuitively after he presents it.
It is a kind of chain rule. It's a kind of chain rule. What you do is you first...
it's a kind of a chain rule. That's interesting.
Differentiate phi.
Because you're looking at the coordinates as functions, I guess.
Phi with respect to the x's. And then you differentiate the x's.
With respect to the y's?
With respect to the y, on the left-hand side, I've picked,
you picked a certain direction. So you're going to take all of them, all the phi's, so each phi with respect to each x, and then take that x and differentiate with respect to the y, with respect to which you are differentiating. So you should have, I think, a bunch of pluses here. So how does phi, so you're looking at it from the point of view of the y coordinate system, so looking at it from a certain y direction relative, so how does phi change relative to a certain y direction? Well, that has to do with the very coordinate system. So it's the phi, how does phi change with respect to a certain one of the x directions, and multiply that by how does the coordinate, this is a line, this is a direction, how does this direction vary relative to this direction. So you need to multiply it. That makes sense. And then you're going to add, so you're going to do a sigma of d phi dx m, where it's a sigma. This is the Einstein notation. But there's no, he just says m. Once he says m and he doesn't mention m, it's sigma m. And that's all that's all it is. So it's fairly intuitive.
So let's see what this means with precision, or not with precision, but in very concrete terms.
Why? Okay, yeah, sure.
For example, what this would say is pick an n.
Exactly. Pick a direction.
Let's pick n equals 1. Mm-hmm. This would say the derivative of phi with respect to y1.
Why is he doing that? I mean, you don't need to simplify it. This is already very straightforward.
This
is the name. This is a coordinate. This is a partial derivative coordinate transformation.
Sum of terms. Note the.
Why would you do that? I mean, n already says everything. Everything is already stated here. It's really this is one example I don't need help with. Other stuff he says I needed help, but with this is so straightforward.
Repeated indices here, so let's write it out explicitly.
Oh my god!
This means
plus
derivative of
phi.
Oh,
wait, what? What do you mean? Okay, well, whatever. Derivative of phi with respect to all the x's. So he needs a sigma. I don't understand what he's doing. Oh, he's going to do the actual plus?
With respect to x1.
Oh my god, don't do that.
The change in x1.
Change, okay. Partial derivative x1. Partial derivative x1 over partial derivative y1.
With respect to y1.
Plus.
Right. Plus, notice.
He's going to go through a bunch of these? I'm going to kill myself. So he's going to go through m equals 2, m equals 3, m equals 4. And then I'll kill myself if he's going to actually write this out.
y1.
Exactly.
I've chosen n equals 1 over here. Plus the change in phi
with respect to x2 times the partial derivative of x2 relative to partial derivative of x1.
I change x2 a little bit times the change in x2.
x2 over y1.
x2 when I change.
Yeah, I was afraid he's going to run out of boardroom. There's no way he has enough room to do all 4. So even after 2, he's dead.
1.
Plus
dot. The change in phi when I change y1 is given by a sum. The shift in phi.
I need to ask her what to do with everything I bought her. She never answered. Oh my god. I'm so terrified of her. Oh my god. Where is it? There it is. Let me see. Mm-hmm. Well, hopefully she doesn't get upset. All right, let's continue.
Phi when I change x1 times the change in x1 when I change y1, plus the change in phi when I change x2 times the change in x2 when I change y1, and so forth and so on.
Yeah, makes
sense. Up to the last term. All right. That's what this means. I could do the same thing with y2. The change in
No,
phi,
he's going to do 2, so y2, y2, y2. Okay.
when I change y2 a little bit, we just have to change the index of the y, not the x's. They're summed over, and so on. What's this formula? What's this called? Do you know?
This is probably maybe the chain rule? Is this the chain rule? Some variation of the chain rule? This is coordinate transformation. But you're treating y as a function, no, you're treating x as a function of y, so it's a chain rule.
Anybody know? I don't know. I don't remember what the name of these rules are.
Is this a total differential? This is not a total differential.
This is a form of chain rule, yes. Okay, so let's write it generally. The change in phi, when you change any component of y, is related to the changes of phi when you change x just by this simple formula. And we can get rid of all of this.
Yeah.
And all we have to do is remember the
Einstein
summation convention. On the right side, m, because it's repeated, is a dummy index. It's not 1, it's not 2, it's summed over. But n, which is not summed over on either side, you get to choose. You can choose n equals 1, you can choose n equals 2, you can choose n equals 3. It's not summed over. And so this is a formula which sort of summarizes all of the derivatives of phi with respect to y in terms of the derivatives of phi with respect to x. All right, let's put these two rules up on the blackboard somewheres, because as I said, they're our fundamental tool for making coordinate transformations. We're interested in coordinate transformations because we want to be able to go from things like curved coordinates to straight coordinates for exactly this reason that we want to.
Why do you want curved coordinates? What do you gain from all this curving coordinates? I don't get it.
Explore how gravity changes when we change our coordinates from curved to straight.
Why do I care?
Or things like that, things of that nature. In fact, in a general space, which is curved, which is itself curved, a space like the surface of a sphere or the surface of a saddle, there is nothing comparable to the rectangular Cartesian coordinates of flat space. We just lay out arbitrary coordinates, and we have to express everything in terms of a set of coordinates which has no preferred special nice straightness in a curved space or curved space-time. And so it's important to learn how to go from one set of coordinates to another, since none of them are particularly preferred. In fact, we're going to want to express the laws of physics in a way which really doesn't depend on the coordinates. But unfortunately, there's no way to write equations without putting some coordinates into them. So we need to explore how you go from one set of coordinates to another. And that's the basic tool of general relativity. All right, so let's.
Strange. I don't see why you need that to talk about gravity. So I think it's not, general relativity is not just gravity, it's everything. It's Maxwell should, I understand that Maxwell comes out of GR, which is very interesting by itself.
Put down the two important facts. The change in a variable when you move from one point to another is equal to
partial d phi dx n times the total dxn. This is where we started when we first started today's show.
Partial derivative of phi with respect to xm, or x, let's call it xm, dxm.
Right. And this is Einstein's notation, so you just add them all up.
Summation convention implied. That's one thing. And the other is that the derivative of phi with respect
to yn is equal to the partial phi with respect to the partial xm times partial xm over partial yn, summation applied.
To, let's call it yn,
Yeah.
can be re-expressed as a sum of derivatives of phi with respect to xn m times dxm
over
by dyn. These are our two governing
summation implied.
little
Good.
simple formulas.
I need to make a snapshot of this when
These are
he's
two
right now. I'm going to make a snapshot. You should make a snapshot of this because this took a long time to derive, so might as well save it. Done. Continue.
governing little simple formulas.
Are you assuming the dimensions stay the same?
What's that?
Between x and y, are the dimensions the same?
Yeah. Yeah, I mean, if we need three coordinates to locate a point in three-dimensional space, it's not going to get only two coordinates or six coordinates if we change coordinate systems.
I don't think
So,
that's what he meant by dimensions. I think he meant like from meters to feet. But fine.
So the number of coordinates is simply the dimension of the space.
Can you say the second equation spells?
What's that?
Can you say the second equation spells for the first?
It probably does. I'm sure it does.
What?
I'm sure it does. Yeah, sure we can. Just change, it does.
What?
Indeed it does.
What it does? Does what? What was the
But I
question?
want to write them both down because we'll be using them regularly. Okay.
Okay, they're both kind of straightforward. The total differential is confusing.
Now, tensors. What are tensors?
All right, let's go tensor.
Tensors are things which have components like vectors, and the components change when you go from one set of coordinates to another. Just as a simple example of a coordinate transformation, let's just do something we're familiar with. Let's take a coordinate transformation from coordinates which look like this. Rectangular coordinates to another set of coordinates which also is rectangular, just by rotating the coordinates as an example. Here's another set of coordinates superimposed on top of the first. And the red ones we can call y, the black ones we can call x. And now let's take a vector. Oh, do I have another color? Let's see if I have another color. Let's take a vector.
It's amazing that after 15 years, this is basically the only GR course in the world.
There's a particular vector. And that is that color visible? Yeah, everybody fine with purple? Okay. That's some specific vector, all right? It has components. Its components we just get in rectangular coordinates. We just get its components by dropping perpendiculars to the axes. And the two components, the x component and the y component. If it's sticking out of the blackboard, there's also a z component. But we simply drop perpendiculars from the tip of the vector down to the coordinate axes, and that defines the components in a familiar way. And of course, the components depend on which coordinates we're using. The coordinates of this vector in the y frame of reference is gotten again by dropping perpendiculars to the axes, but they're different axes. So the components of a vector do depend, in general, they depend curvilinear or not curvilinear. They do depend on the coordinate frame, and there are rules that you can work out easily, we're going to talk about them, for relating the coordinates of a vector in one frame of reference to the coordinates in another frame of reference. If we have some vector equation, an equation that some vector is equal to some other vector, then the only way to express it with equations is to express it in terms of components. But we want to make sure that's an equation which is true in all reference frames. And so we have to know how to go back and forth components of things. So a vector is one thing which has components.
So the idea is to be able to switch between reference frames. Okay. I don't see how general relativity has to do with that, but fine.
And how many components does a vector have? Again, in a d-dimensional space,
D components.
you can think d equals 3 if you like, but in a d-dimensional space, the number of components that a vector has is d.
Of course.
Uh,
Amazing. 15 years ago, he was already an old man. So, but he's still up and running. This guy. And this is like every time he comes to class, it's after jogging. Like one time, he actually came with shorts and jogging sneakers.
A vector is a special case of a tensor. It's a tensor with only one index.
This is where I get lost. A tensor. Okay, forget it. Whatever. Let's let him explain. Maybe we'll have to watch more videos about tensors. Maybe he's not going to explain it well. I hate it when they say a vector is a special case of a tensor. It's a tensor with only one index. I don't know what you mean by that. I don't know what you mean. I guess like a tensor is a 4x4. What? I mean, what is it? What he never defined a tensor. All he's saying now, before he defines a tensor, he says, well, a vector is a tensor with only one index. Okay. So a tensor has how many indices?
Or a tensor of rank 1. All right.
Okay.
A simpler thing, which is also a tensor, but which is even simpler, is a scalar. A scalar is a quantity which really doesn't have components. It doesn't have a sense
it has one component.
of directionality. It's just a number, a numerical value. It doesn't have any components. When I write down the scalar phi, let's suppose that phi is a scalar. It doesn't have to be in that equation, but let's suppose that phi is a scalar. Then that scalar has a numerical value at every point. And
yeah, like a mountain terrain. What is the height?
that, like, for example, the temperature. The temperature in space doesn't depend on whether I choose coordinates one way or the other. It's a scalar. But it's a special case of a tensor, and it's a tensor with no index.
Nothing cares what coordinates you're using. The coordinates are projected on reality, but reality is one. You can look at reality from different coordinate systems, from different frames of reference. I could be moving, looking at reality. You could be standing, looking at reality. Reality is one of the same. So whatever it is you're describing should have nothing to do with the frame of reference.
Indices. It has no indices
Oh, it actually does because of special relativity. It actually does.
at all. It's a tensor of rank 0.
So scalar is a tensor of rank 0. A vector is a tensor of rank 1. I guess a matrix is a tensor of rank 2, and a tensor is rank 3, or maybe more.
A vector is a tensor of rank 1. We're going to explore quantities which are tensors with any number of indices. And these things are more obscure. They're harder to understand geometrically, but eventually you'll get familiar with them. And the rules for them we can work out by starting. The best place to start is with scalars. Let's start.
Let me just make sure everything is fine. Okay, I think we survived this message, but you can never know.
Start with scalars and talk about how they transform from frame of reference to frame of reference. Well, the answer is they don't. They stay the same.
Exactly.
So we could write that in the following, notation. The field phi in conventions in which we use coordinates y to describe it. Let's call it phi of y.
Should be invariant to whether it's y or x. So I think we should have a notation of some equal to invariant relative to phi of x or something.
Is equal to phi of x. If x and y here label the same point.
I see. Okay, that's good.
This is the expression for phi in the x coordinates. These are the x coordinates. Here's the y coordinates laid down. I'm going to draw them over here. There's the y coordinates. And let's suppose that this point and this point really are the same point.
Very good.
Then there's only one value of phi. It's the value of phi at that point. And the transformation property of a scalar is trivial. Nothing happens to it. The temperature at a point of space doesn't depend on which way the coordinate axes, or even if you're using curved coordinates. And so this is the transformation property of a scalar. Okay. Now let's come to a vector. How do the components of a vector transform when you go from one frame of reference to another? We need to start with some vector. We need some quantity which is a vector.
So it's 2 points. A vector is defined by 2 points.
And a simple vector, perhaps in many respects the simplest vector, the primordial vector in a sense, is a little displacement. A little displacement, namely the thing that we already called d phi, dx, excuse me. Dx represents a vector, and we can put an arrow on top of it to indicate that it's a vector. It's nice to indicate vectors by arrows. And it simply means a little differential displacement. It's a sort of quintessential vector, a little small displacement.
Okay.
Okay. Now, it has components. This stands for the vector itself. The vector itself is a geometric object. It has components. The components of it are just dx1, dx2,
Comma.
dx3, and so forth. In other words, the components of it are just the little displacements in the x-coordinate frame. So again, if this is the x-coordinate frame, and this is dx, then these dx's are just the little displacements of the coordinates themselves. Right? That same vector can be described in y coordinates. The same physical vector. Think of the vector as a little stick with a pointer on it. That same physical vector has components in the y coordinate frame. And the question is, how do we find them? Those components are, starting at this point and ending at this point, the components are dy1. I've written it as if it were three-dimensional space, but as many as you like. It's the same vector, but with the components being expressed relative to two different coordinate systems. What's the relationship between them? Well, let's suppose we go from...
Well, we already wrote out how to convert from one coordinate system to another.
From one point to another, and let me focus, remember, these y's here are all functions of x, and the x's are also functions of the y.
That's incredible.
They're functions of each other. The x's and y's are functions of each other.
Right, but you can treat them each as independent. You can say, okay, the x's are independent or the y's are independent.
Let's concentrate on dy1 over here. What's the change in y1 when I change x by a little bit?
It's d phi. What is dy1 when you change x by a little bit? What?
For that, I use the top equation, except phi now being replaced by y1. The change in y1, now we're just going to repeat that equation.
Wow. So y is the function relative to x. So it's d phi dy dy dx. So just the phi dy, which
is the derivative.
one second, I want to guess it. So this is dy1. So you have to go, and it's relative to a change in x. So it's x1, x2, all the x's are being changed a little bit. So it's d phi dy1 dx dy1 is equal to d phi relative to dy1, but dy1 is relative to partial dy1 relative to partial dx1. And then you're going to do it plus the same thing relative to dx2. And the same thing plus everything relative to dx3, dx4. Okay.
Change in y1.
D phi, partial d phi dy1.
I'm just going to repeat that equation. Is the derivative of y1.
Wait, oh, sorry, there's no phi. dy1 relative to dx, and it's going to be x, this time dx1 times partial dx1. No, it's going to be times dx1, total dx1 times total dx1. Yeah. So d phi, partial d phi 1 relative to partial dx1.
With respect to xm.
Okay, xm multiplied by total xm. So total dxm. So regular dxm.
dxm.
And that's it. That's already a summation over all m's. 1, 2, 3, 4. That's how the coordinate y1, this is the total y1. So what does it mean? So you want to walk, so you want to view the new coordinate system as the function. And let's say y, this is y1. So you want to talk about dy1. If I walk a little bit on dy1, no. The question is, what happens to dy1 as I change the x, as I move from this point? So I move a little bit of dx, a little bit of dx1, a little bit of dx2, a little bit of dx3. I move a little bit in the positive total dx. So what happened to y as I did that? So let's say I moved from here a little bit to here, a little bit to here, and a little bit up. So what happened to y? What happened to y1? So I moved from y1 over here to some y1 over here. So basically I moved from 0 to some place over here. That's what happened to y1, I think.
You get it? The change in y1, I'm just using that exact formula up on the top, except with phi being y1. The change in y1, when I move in x space a little bit, is just the derivative of y with respect to x times the change in x, summed over m. What if I were changing y2?
The question is, what is dy1 dx1? So y1 relative to x1, as you can tell, so in what is the ratio? As you move a little bit along x1, how much are you moving along y1? I would say it's cosine, it's dot, it's the dot product. Y1, x1 are dot products. I think. I don't know. This is really confusing. I don't know what he's trying to accomplish.
Well, what would be the change in y2 when I go from one point to another? I just replace
Obviously,
the
it's
2 up here.
place, but I'm thinking. I mean, y is not really. Yeah, it is a function. You can look at y1. This is y2. You can look at y2 as a function in the x space. But what is it? Is this line? Is this line is y2, or is this line y? Which line is it? I don't know.
What if I pick a generic index n? Then it just becomes the differential displacement in yn
Yep.
just the derivative of yn with respect to xm times dxm. All right? Well, this tells me explicitly how the components of the small vector transform. They transform by getting multiplied by this collection of things dy by dx. Now I can tell you what the definition of a contravariant vector is.
Contravariant vector. I guess it's the transformation of a vector from one coordinate system to another.
The definition of a contravariant vector is a collection of things which have components in both the x frame of reference and also components in the y frame of reference. And those
I wish he could show this in 3D animation. What is he trying to show here?
components, let's now be general.
This is really difficult to imagine. I'm unable to imagine exactly what he got here.
General, let's call it V for vector.
Vector
The components of the vector, V1
is dy. Well, in this case, is dy. It's just dy.
through Vn in the y frame of reference. Let me put down here in brackets that these are the components relative to the y frame of reference. In other words, relative to the y coordinate system are equal
Why don't you show the vector?
to the derivative of yn with respect to xm times vm in the x coordinate frame. In other words, they behave exactly the same way as.
So this is already all the dimensions. So the bottom one is in all dimensions. So it gives you the vector form. The top one is just one dimension. The bottom one is all the combined dimensions. So the top one is true in each dimension. The bottom one is the full vector expression.
As these little differential vector components of a little displacement.
Right. The top one is the components. The bottom one is the vector itself.
Now, don't ask me why this is true. This is definition.
This is not definition. What do you mean this is different? Oh, the definition of a covariant vector. This is the translation of a vector from one coordinate to another. Okay.
This is definition of an object which transforms
from the y to the x coordinate system.
Contravariantly.
Well, usually we say invariant. That means there's no change when we look at it from different perspectives. What is contravariant?
It's just a word. It doesn't, for our purposes, it doesn't mean anything right now. That's the definition of a vector or a contravariant vector, that its components, whatever they are, that they transform when you go from one frame of reference to another through this collection of quantities, dx, dyn by dxm. How many quantities like there are there altogether?
As many dimensions as you want. What do you mean? Oh. I mean, so I don't know what you mean. How many? Because in this equation, the top equation, this is the summation over m dimensions. But there is n dimensions, which is the same number. So let's say it's 4. So there's 4 of these, but there's 4 of these, so that's 16. But I don't know if that's what you mean. I just don't know. So this is the vector notation, and when you write it out once and then you write it out in full, you're going to get 16 terms. But I don't know what you mean, how many, whatever.
D squared. Right. Any y can be differentiated with respect to any x.
So if it's 4 dimensions, time and 3 space, that's 4 dimensions, times 4 is 16.
Yes. And so there are d squared such coefficient functions here. And this is the way you transform a vector. To those who are familiar with linear algebra, this is, of course, a matrix. And this is a column vector, and here's a column vector, but we don't need that right now.
Oh, that's a matrix. Oh, so it's a transformation it's a matrix transformation from one coordinate system to the other. Okay, interesting. So this is the beginning of Einstein's notation for all the dimensions.
Now, this is the transformation property of a contravariant vector.
Does contravariant refer to the nature of the coordinate system?
No, it refers to the way it transforms. The way it transforms, that's right. The way it transforms. We're going to discover other objects called covariant tensors. But so far, this is just a mere vector, something that's pretty easy to visualize. Now, a tensor of rank 2 is an object which is not so easy to visualize. You should think of it somehow as having 2 directions, so that's a thing that has built into it 2 directions instead of 1. But there's an easy way to think about this. The simplest tensor that's made up, the simplest tensor of rank 2 can be simply thought of as a product of 2 vectors. Given 2 vectors, and they could be the same vector or they could be different vectors, it doesn't matter.
Product of 2 vectors? What could that be?
Let's call one of them A, and it has components M, A sub A, M. And now let's take another vector, which we'll call B, and write its components down. How many such things are there altogether?
What do you mean?
I can multiply. There's a whole collection of objects I can make up. I can take any one of the components of A and multiply it by any one of the components of B, and that's an object. It's an object that may or may not be interesting. We're going to discover ones which are interesting. How many such components does such an object have? This has D components. This has D components. The number of components altogether is D squared. So this is an object which has D squared components, and the individual components are labeled with 2 directions. This is a special case of a tensor of rank 2.
Oh,
It has 2 components.
this is the lambda or it's the T? This is TMN. I don't know what he's talking about right now.
Sorry, it has 2 indices, and altogether D squared individual components.
It's a very problematic way to teach this way. It's like, I don't know where he's going. He's always going into the unknown. It's not like when I would teach something, I wouldn't start from the unknown and go into the unknown. I would try to always relate it to something physical. Like, oh my God, this is so difficult to follow.
How does it transform when I change coordinate systems? Well, this is easy. I already know how the vectors transform. So all I need to do is...
What do you mean? A is a vector and B is a vector? And T is... I don't know what he's talking about. What is A? I don't know. What is A? What is B? What is T? TMN? I don't know what's going on. A I think A is a vector in 4 dimensions. B is a vector in 4 dimensions, but AM is A in a certain direction. BN is B in a certain direction, a certain component. This component times that component is some T, which I don't know what that is, but it's some object that is composed of the MN. So it's called TMN, and that just means the product, or I don't know what. He didn't say what, like product or addition or who knows, or division of AM by BN, but he didn't say what the transformation is.
Let's work it out. Let's work it out. Let's take let's compute AN AM BN in the y frame of reference. In other words, where the coordinates.
What are we doing here? So, okay, we have AM and BN in the y coordinate system.
Are written relative to the y frame of reference. Well, here's a rule for connecting components of a vector in the y frame with components of the same vector in the x frame. So let's just apply it. Let's relate these. Now, first of all, there's A. A is a vector are not dummy indices. They're picked.
I guess it's after the break or something, but he forgot to start the camera, so we got started late. 1 second. Let me pour some whiskey. I need to drink my whiskey. Whiskey and gin and rum. Ugh. I need my whiskey and my rum. My whiskey and my rum.
Could be 3, this could be 2, but they're not summed over. The dummy index is one which is summed over. All right, so here's the matching. This index matches this index, so we better put an M up here. And then we differentiate it with respect to a dummy index. I don't want to call a dummy index N now, so I'll call it.
I don't know what he's doing. So he's converting. So let's
matches this index.
Okay, we need this equation, so let's take it. Take it. Okay, copied over. So this is so we're going to be converting a vector's component N to a vector component M. This is N and this is M. This is Y and this is X. So the nth component is YN, XM. Okay, so when you take a component of a vector in Y space, you want to convert it to the. 1 second. Oh my God, my battery is garbage. It's not charging. How unfortunate. Yeah, my batteries fell on the floor way too many times. I think they're broken at this point. They're almost completely dead. Okay, so given a vector component, we can convert it to multiple vector components, not just to one. Or we can express it as vector components in another space from Y to X.
So we better put an M up here. And then we.
Okay, so we're trying to convert. What are we converting? We're converting. I think he's starting with A. So let me think. So A component M in the Y, we want to express it in X. So it's going to be A. It's going to be dy m. Well, I'm just following the notation. So it's going to be dym dx n vn in the x component. That's going to be a. Let's see what he does.
All right, so here's the matching. This index matches this index.
Right.
So we better put an m up here.
Yes.
And then we differentiate it with respect to a dummy index. I don't want to call a dummy index n now.
What are you going to call
So
it?
I'll call it xr.
R. Okay. So if that's R, then you're going to have multiplied by VR in the X space.
Times AR. That's
Oh, right. Not VR. V is the vector. AR in the X space.
just this piece of it over here. AM of Y, this should be of X.
Yes.
AM in the Y
Now you're going to do the same with BN and B.
frame of reference is
Multiply.
the derivative of ym with respect to xr times ar summed over r. Now that's only half the expression. The other half involves what happens to b.
So
let's write that
multiplied
down.
by.
Again, we should match indices.
So
Here we have
Bn is going to be partial y, partial dyn.
the nth index, so that means some derivative of y
n divided by partial dx. You could use r. I don't know if he's going. I think he can use r. I think he's allowed to use r.
Now I need another dummy index.
So q, rq,
I need another dummy index. I've already
s.
summed over r. I can't call it r again. So I'll call it s. xs.
Then b. Bn.
Times dx.
No. No. Times Bn at x.
Times a
No, B.
times b.
Bn in x space.
S.
Bs. No, Bn. Bs. Bs.
In the x reference frame.
Exactly.
All I've done
Oh my God, this, I don't know where he's taking this. If I only knew.
is taken a and b and separately transform them from the x coordinates to the y coordinates. But now let me just regroup it. Let me just regroup it by taking
What do you mean regroup? I think you.
this over here,
Yeah. Oh, are they similar?
writing ARX.
What do you mean? Why did you do that? Oh, because it's everything is multiplied. Okay.
AM times BN
AN times BN, AM times BN,
is called TMN.
TMN.
A tensor of rank 2
Oh, tensor MN. Oh, okay. This is a tensor of rank 2. Tensor MN.
with index m and n. So I can call this then TMN
Is equal to.
with components in the y frame of reference. That's equal to dym by dxr dyn by dxs. And what shall I call this?
T, I guess. You have to say it's S, so it's TS in X times TR in S in X. If you call that T, then you call
It's also some t. It's also the components of a tensor built up out of a times b. Okay? Not TMN, but TRS. TRS.
Yes.
The first entry has to do with A, the second entry has to do with B, so I should really invert the order of them.
Oh my
B,
God.
S, X, just to make it look the same as on this side. And then what do we see on the right-hand side? On the right-hand
TRS.
side, we have TRS
X.
evaluated, or its components in the X frame of
Oh
reference.
my God.
So this little operation has defined for me a new class of things, which are tensors of rank 2, which transform in this manner. Notice it's very similar, except sort of doubled. Each time you want to transform an index, you get a factor dy by dx. For each index, here's the index m. You have a dym by dxr, and this is a dummy index. And then
I don't know if Einstein understood this because he had to learn this just as we're learning it now. So I don't know if he ever understood this. We know that he made a complete mess out of everything. So we might be ahead of him right now.
for the n, you'll have a dyn by dxs, and then it multiplies the t with the rs index in the other frame of reference.
But Lenny Susskind, I mean, he should know this, but he still doesn't understand relativity. I don't know what's going on with these people.
This is a pattern.
I don't know what's going on here with the tensor. I honestly don't know. This is way over my head, or way over my pay grade. I don't know what's going on. Tensor, schmenser. What is this tensor? I don't know. I don't know what's going on.
You could do the same thing for tensors with any number of indices up here.
Oh my God.
I'll leave it to you to work out the rules.
Leave it to me to kill myself.
They're easy. They're just simple generalizations of this, where for every index, you get another factor like this and another index up in the tensor over here. That's all a tensor is. That's the whole definition of a tensor. These tensors are generally functions of position. They're functions of position in general, just like vectors can be vector fields and vary from place to place. But this is the rule for transforming tensors, and that's all there is to it. There's no other definition of a tensor than this. And we're going to see some examples of them. Rather than try to give you a deep geometric insight into them, I think we'll work with them for a while, get familiar with the machinery for them, but we're going to see some examples of them. Okay, so that's the definition of a tensor with contravariant components.
I mean, I learned to use tensors many thousands of years ago. This has nothing to do with it. Tensors are very good when you try to analyze deformations of mechanical units under stress, under strain, under shear, under forces. Like you always wonder, okay, what happens to this under this force? What happens to that under that force and stuff like that? You always want to know how things deform. That's very important. So we use tensors for that. But I don't know which sounds similar to what Einstein is trying to accomplish with GR. But I don't know what to say.
We're going to come to what a covariant tensor is, and you'll understand the difference. But all of these indices are transforming the same way. They're transforming with coefficients dy by dx. Not dx by dy, but dy by dx. When you want a thing in the y frame on the left-hand side, then it's dy by dx on the right-hand side times tx. All right, that's the definition of tensors with all.
That's not a definition of a tensor. I don't know what this is. How is this a definition of a tensor? My God. This is tensor conversion between spaces.
All contravariant indices. Next, let's see.
Wow, this is the worst lesson I've had in my entire life. I have no idea where he's taking this.
Should we take a break or should we take a break
We kill ourselves? Yeah, definitely.
in another 10 minutes?
I actually have a question on this.
Mhm.
When you make those rearrangements, right, you've made a lot of assumptions about the math behind it, right, the tensors, right? Well, I mean, you assume they're commutative, and it's not a cross product, not a dot product.
Yeah, no, this is just numerical multiplications. Yeah.
Always eating a cookie.
No, there's nothing.
Nom 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 nom.
You can invert the order.
He's going to drink the coffee without the cap. Why would you do that? That makes no sense.
Of anything times anything else as
It's
long as you
it's gonna get cold. It's more difficult to drink. You're gonna spill it. Why would you do that? This doesn't make any sense. It's gonna get cold.
just multiplying numbers, and each expression on the blackboard is a number.
Gulu, 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 gulu. What is he drinking? It's not. Is it hot coffee? What's going on?
Some assumptions in there. The matrices should be invertible.
The matrix. Is there a matrix here? Did he say matrix? So T is a matrix.
Right.
I mean, these are matrices, and they are invertible. The assumption that they're invertible is equivalent to the statement that there's one-to-one mapping from X to Y and from Y to X,
Well, that's the assumption.
that you can invert the coordinates.
Obviously, it's just the frame of reference. Reality is the same.
The thing is that you have your first rule is basically a total differential, and that means that it has to be exact.
Yeah, that just means
Of course, it has to be exact. It's just math. What do you mean?
it's a function. It means it has a value everywhere, well-defined value everywhere, that's all.
Yeah. What are these guys asking? I don't even know what they're asking. I don't know what he's teaching. I don't know what's going on.
Well,
No.
it means that the partials have to have good quality.
No. Well,
What's a good quality? What does that even mean?
assuming everything is differentiable, that's all you have to assume.
Twice.
Okay, we have a message. Maybe it's a sign you shouldn't be. Every time I wish to eject my family member. What is going on here? Oh my God. Oh my God. What is going on? What is going on?
Twice differentiable.
And they
Yeah.
can mix.
And what?
You can switch the order,
Then you can switch the order of differentiation.
and you're good.
Right.
1 second. Let me give everyone. The link. The link. The link. The link. Here you go. Here is the link. Take the link. Take it. Take it. Take the link. Take it. Take the link. Take it. Okay, you have the link. You know what to do. You know what to do. You know what to do. You know what to do with your life. You know what to do with your life. Your life. Wait, what did I just give you? That link? Okay, let's take this link. La 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 la. Okay, that's good enough. Let's continue with our lives.
All right, let's spend a few more minutes and spend a few more minutes with the idea of a covariant vector.
Vector. I don't know where
The
he's
top
taking
thing,
this.
d phi is the archetype of a contravariant vector. D phi, or sorry, dx. dx is the archetype of a contravariant vector. It has components, and its components are simply this. Here's another object with components. How many components does it have? It's the collection of partial derivatives of phi. It also has d components, has the same number of components as dx here. It's also an object that one could call a vector.
Yeah, we need to figure this out. We never got an answer. Oh my God, what is going on? So what did we decide? Did we decide, what's his name? This one. Um, um, so what did they say? Oh my God, I don't know what to do with these people. I need to coordinate. Um, I don't know what to do. Mm, so what did we say? So, mhm. um, mhm. Forget it. I'm not going to react right now. It's impossible. Too many unknowns right now. What's this? What is this? 1 second. Oh, so this is the original. Okay. That's good. Okay.
Insofar as it has components, but it's a geometrically different kind of thing. It's not a displacement, but it's the gradient of a function. It's the rate of change of a function along different directions. An object like this is called a covariant vector. More precisely, they're called the covariant components of a covariant vector.
What is he trying to say? I
Vector.
don't understand what he's trying
But
to say.
we can also ask, given a collection of objects defined by dxn, here they are, defined by dxn, here's a collection in the x frame of reference, how do they transform? In other words, if I gave you this covariant vector, namely d phi by dx, the collection of components, how do I calculate d phi by dy? Well, here's the rule.
Yeah,
Here's the rule right here. I don't need to go any further.
right.
And I can abstract from this rule a more general idea of a covariant vector. Instead of taking d phi by dxm, let's just define an object to be a covariant vector if it transforms in the following way. I guess I can use the same letters.
It's going to get worse and worse and worse. Where is he going with this? I don't understand where he's going with this.
I'll use the same letters, but now we're talking.
One except upside down.
What's that?
It's kind of the same thing as the.
Yes. We're going to compare the two in a minute. All right, so here is A. I'm going to put its index downstairs. Why? Just because it looks nice. This is down lower than, but there's a real reason. There's a real point. We'll come to it for a moment. in a moment. But when you write covariant indices,
Oh,
you
there's
always
covariant and contravariant. I'm so confused.
write them downstairs. When you write contravariant indices, you always write them upstairs. The difference between the covariant and the contravariant are how things transform. So here's an example of a covariant object, which it's just a definition now that we put the index downstairs. It turns
Covariant downstairs, contravariant upstairs.
out to be a nice definition, a nice notation. It's a notation, it's not a definition. A sub n in the y frame of reference.
So he's just switching upstairs and downstairs notations.
Its components in the y frame of reference are equal to dxm by dyn times a sub m in the x frame of reference. These are the components in the y frame. These are the components in the x frame. d phi by dx is the component of a in the x frame, d phi by dy in the y.
I have no idea what's going on. So a vector A in the y space converted from a vector A in the x space. So the nth component of vector A, you get it from the partial delta of x to y, xm. How does m, and you're going to go through how delta, you're gonna take partial delta x to partial delta y. So you want to get the nth component. So you're going to take the partial of all, I think all the m's to just to that y. So you want, then you multiply by that part of the vector in space x, the component in the m direction. I don't know.
Y frame. All I've done is abstract out of this, replace d phi by dy.
Let me see the other vector. Did we get the other vector? V. Well, everything is upside down. I don't know what's going on. Oh my God, this is so confusing.
By a, and d phi by dx also by a. And this now defines a class of objects which may be more general than just gradients. Any object whose transformation property is like this is called a covariant vector.
Oh my.
So let's just look at the difference between the transformation properties of covariant and contravariant vectors. I'll use this as my typical contravariant vector. And now let's write the corresponding thing for the covariant vector.
Okay, at least
an in the y frame of reference is now equal to dx by dy n m, or let's call it r.
so. This is moving backwards.
I guess I can call it m times a m.
No, this is still, you're moving from x to y. So what is different? You're still moving from x to y. But the question is, how could it be that you're using a different, how could it equal something different?
In the x frame of reference. Notice the difference. One of them involves the set of derivatives dy by dx. The other involves a set of derivatives dx by dy.
How?
Notice that there's a very nice pattern here. The index upstairs is upstairs on both sides of the equation. And when you contract or when you sum over indices using the Einstein summation convention, it's always an upper index with a lower index. That's a general rule, that when you sum over indices, you should be summing over indices one upstairs and one downstairs.
Yeah, but that's not what you're doing.
There's something wrong with your equations if you're identifying indices and summing with both of them either upstairs or downstairs. But thus far,
So how do you explain this? You're summing over m's. They're both upstairs.
it's just a notational device. And we see it has that pattern that a thing which is downstairs on the left is also downstairs on the right. And when we sum over a dummy index, it's always an upper one with a lower one, which is a sort
Oh, that's upper with lower.
of cancellation. An upper one cancels a lower one and gets rid of it, so to speak. That's the pattern. There's no theorem here. It's just an observation about these equations.
What are these equations? My God.
And these are the two transformation properties. And once I have the idea about how a covariant vector transforms, I can define objects which have several covariant indices. Covariant indices mean indices downstairs. And I'll give you an example. Same deal. Exactly the same deal. I go through the same thing except with covariant indices. And let's see if we can figure out or guess what the transformation properties of a tensor with two covariant indices is.
Yeah, this is
All right, so
just
now it's two covariant
too
indices.
painful.
This is the y.
Oh my God, this is too painful. This is just incomprehensible. I don't know what's going on. It's just incomprehensible.
In the y frame of reference. We have to turn the derivatives upside down.
Okay, let's see, how long have we been here? An hour and a half. I think we're going to take a break, even though we didn't finish. Usually I go through these lectures really fast because everything is so straightforward. But this lecture is impossible.
They become dx by dy instead of dy by dx.
I don't have a geometric interpretation of what he's trying to do. That's the problem.
And on the right-hand side, we also should have lower indices, rs, x. We have a tensor with two downstairs. You know, incidentally, I don't believe I've ever in my life heard a physicist actually refer to covariant indices and contravariant indices. We just call them upstairs and downstairs, because nobody can ever remember which is which. I looked it up tonight so that I get it right, but every time I do, I forget the next time. Incidentally, what do I have here? Let's put the indices in. There's lower indices here. Better mean there are upper indices here if we're going to sum over them. And there's lower indices here, so there better be an m and an n.
It's R and S.
R and S.
Oh, R and S. Thank you.
You know what it is?
Yeah.
I think partial derivatives are in some sense like basis vectors.
They are.
And so varying like the basis
What is a basis vector?
vectors is covariant.
Mm-hmm.
That's where that terminology.
Okay, that guy knows everything apparently, because I have no idea what's going on.
Perhaps. Where the contra came from, I don't know. But you can check the pattern of these things. There's always a pattern to them. When you sum over indices, it's an upstairs with a downstairs, upstairs with downstairs. The left-hand side here has downstairs indices, m and n, and so it's not too hard to keep track of. And by inspection, you can see whether your equations make good sense in this respect. Okay, let's take a break, and then we'll come to the metric tensor. The metric tensor itself, the metric tensor is a tensor and it's an important one. Okay, let's get started. I think I'm going slowly. I hope I'm going slowly.
No, you're not going slowly. I have no idea where you're going, and you're not giving any geometric interpretations.
I'm going intentionally slowly, which means I'm telling you things that many of you already know, but I'm going at a rate which I'm hoping will carry along the majority of you. We now want to come to the idea of a metric tensor. Let's begin with ordinary conventional, I will call it by its right name, flat space. Incidentally, let's distinguish two things. There is flat space, which I have not defined for you yet, but the tabletop here is a flat space. The blackboard is a flat space. The surface of a sphere is not a
Flat space just means where there is no gravity. Where there is gravity, there is acceleration. Acceleration is curved space. That's what they mean. But I don't care. For me, it's the flow of the ether.
flat space.
And the ether is accelerating because of Gauss's theorem.
And there are flat coordinates.
He already went through this in the previous lecture, so I already know that my intuition is aligned with what he describes. At the end, Einstein has to agree with Newton. So Newton already is Gaussian. Is Gaussian flow. So that's all I need to know.
Flat coordinates usually are taken to mean, when people speak about flat coordinates, it's usually it's an abuse of language. But what they mean is rectilinear, pretty much Cartesian coordinates, sometimes spoken of as flat coordinates. The axes are not curved, the axes are flat, and so forth. So we can speak of flat coordinates, and we can speak of flat spacetimes, or flat spaces for the moment. All we're doing is space now, not space-time. Quite a distinct concept. You can introduce, as we will do it, we can introduce, for the discussion of flat space, there's nothing to prevent us from using curvilinear coordinates on it. On the other hand, there's no clear concept of flat coordinates on curved space. Curved space, you can coordinatize it, you can lay down coordinates on it, but there's no sense in which one set of coordinates is any straighter than the other set of coordinates. And so I thought I would just point that out to you. In a curved space, it's basically a space which has an obstruction in it, a mathematical obstruction, to using flat coordinates. This word obstruction I'm using over and over again, and I do want you to think of it as being related to the obstruction in removing a gravitational field by changing coordinates. Here in geometry, it's a question of whether, well, let's write down what the metric is first, and then I'll tell you exactly what it's an obstruction to, what curvature is an obstruction to. Does everybody know what I mean by the word obstruction? I mean a mathematical property that forbids you from doing something to simplify a situation in a certain way. Okay, let's start with flat space. I'll draw it, of course, as two-dimensional, and I will introduce some coordinates. And I'm going to take the simplest set of coordinates, Cartesian coordinates. It is not important for us whether they're tilted this way or that way. We can rotate the coordinates. But let's take an infinitesimal vector dx and think of the length of the vector. All right, I'm going to take the square of the length of the vector. In 2 dimensions, we can just drop perpendiculars and rewrite the length of the vector in terms of the components. This is, of course, also true in higher dimensions, 3, 4, 5 dimensions. And we use the Pythagorean theorem let's call the length of the vector, let's call it ds. It's also small, so it's also differential. And the Pythagorean theorem for 2 dimensions here would say that the square, it's just the square of the hypotenuse, we call it ds squared, is equal, in this case, to dx1 squared plus dx2 squared. Now, please, let's not confuse notation. These superscripts over here are labeling which coordinate we're talking about. This superscript over here literally means square. dx2 here does not mean anything squared. It just means the second coordinate. This means the first coordinate. So I'm putting them in brackets just so you'll know. If I didn't put them in brackets, you would think it was dx12 or dx22. So I put them in brackets. That's the Pythagorean theorem. If there were more coordinates in a higher dimensional space, and we were using Cartesian coordinates, we would write dx3 squared here and so forth. Okay, let me write this in another way for you, which is sort of slightly contrived. I don't know, maybe it's not so contrived. First of all, I can write it in this fashion. dxm dxm. Now, this is violating one of my rules about repeated indices. My rule about repeated indices is that you should put one upstairs and one downstairs. Okay? So I'm explicitly violating that rule, but in order to, I'll just remind myself that it really means sum over m. And this means dx1 squared plus dx2 squared plus dx3 squared. And as I said, I've explicitly violated a rule which I set out, but I want to restore that rule. I want to rewrite the same equation in a way which restores the rule. And so I'm going to invent a new symbol. What's the new symbol? Anybody know what it is? Not eta.
Lambda.
Kronecker, delta.
Oh.
Right. 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 Eta is the other symbol.
Eta? No, we're not using eta.
The mathematical symbol delta mn. That mathematical symbol has the following meaning. It is, how many components does it have altogether? D squared. Each m and each n, it has a value. Its value is equal to, its numerical value is equal to 1 if and only if, IFF means if and only if, m is equal to n. In other words, delta 1, 1, delta 2, 2, delta 3, 3 are all equal to 1. And it's equal to 0
Otherwise,
if and only if m is not equal to n. So that means delta 1, 1 is equal to 1. Delta 2, 2 is equal to 1. Delta 3, 3 is equal to 1. Delta 1, 2 is equal to 0. Delta 1, 3 is equal to 0. Delta 3, 2 is equal to 0. That's the meaning of the symbol, mathematical symbol. And, you know, it's partly some interesting mathematics and partly simply notation, a notational device to be used to simplify equations. All right, now, I can rewrite this in the following form. Notice I've put these indices downstairs. All right. I'm going to rewrite this as equal to delta mn, with 2 downstairs indices, dxm dxn with 2 upstairs indices. Let's see what this thing means.
Mm-hmm.
It means, and m and n are both summation indices now.
Interesting.
They're both summation indices. 1 upstairs and 1 downstairs, 1 upstairs, 1 downstairs, 1 upstairs, 1 downstairs, 1 upstairs. So this now conforms to my rule about the way that you combine indices together. If you want to sum over a repeated index, make sure 1 is upstairs and 1 is downstairs. Now, what does this give you? Well, every time m is equal to n, delta mn is 1.
So it's
So that gives you things like delta dx1 squared plus dx2 squared plus dx3 squared and so
otherwise
forth.
it's 0.
In other words, when m is equal to n, you get a dx squared, and you get one for each numerical value of m. Okay? What about when m is not equal to n? Are there any terms in here with dx1 times dx2?
No.
No, because delta 1, 2 is equal to 0. So this expression here, that's the purpose of delta mn, is to pick out the contributions when this m is equal to this n, and that means just summing the squares of the dx's. That's what a delta mn, and it simply restores the rule. Writing it in this way restores the rule that when you use the summation convention, you should always be summing over one upper and one lower index. All right, so here's a neat form for ds squared. Delta mn dxm dxn. But now I want to write this. I want to write the length of this vector not in x coordinates, excuse me, not in x coordinates, but in y coordinates. The same little vector, the same precise little vector, which has exactly the same length, but I want to write it now in terms of the differential displacements in some other coordinates. In particular, I have in mind curvilinear coordinates of some kind. So let's rewrite the same expression.
So there's
What
4
we
people watching us right now? Jesus.
need is a formula. Let's erase the blackboard here. We need a formula for dxm, for example, this one over here.
Yeah,
In terms,
thank you, cameraman, for not showing us what he's pointing at. But I think it's the ds squared is equal to the sum of dxm squared. So we want to. What do we want to say about dxm?
of dy's.
Right, we want to express dxm in terms of dy's. dy, I guess, ends.
If I had that, I could plug it into here and re-express this in terms of the dy's. So what do we know about dxm? For that, we use the top formula up on top. Let's see. Except with x's being replacing y's. All right, I'm going to write the formula. I think you'll all recognize it.
Yeah,
The
please.
change in xm when I move from one point to
Okay,
another.
so it's partial d. The change in xm in terms of y. Well, it's how xm changes. It's the partial xm, sorry, dxm, partial dy, but which y? dyn times total dyn summed over.
Another
Partial
is equal to the derivative
xm
of xm
relative to partial dyn.
with respect to yr.
Okay, fine. R times total dyr.
dyr.
Right.
This is an application of the rule up on top,
Yes.
except where there are y's here
Phi is x.
instead of x's. And where the thing which is changing, d phi, is just xm.
That's good.
Same rule, a change in a certain
So confusing. Jesus help us.
quantity is the derivative of the quantity with respect to y times the change in y summed over the components. All right, so that's all we need to do now. We can now rewrite this distance
Pythagorean.
in y notation.
Okay.
Let's do it. Here it is, ds squared is equal.
Lambda mn, I would say.
Let's see what we have. Delta mn.
Oh, it's called delta, not lambda? Really? That's a delta? Okay. Delta mn.
That's
Now we need dxm.
this. Now we have dxm. That's this.
That's just that. Okay. Just copy it.
Partial of xm with respect to yr times dyr, but I'll write
You're not going to write dyr?
dyr in a moment. I don't want to write it down yet. Yeah, let's put it over here. dyr.
What is he going to add?
But now we also have to put in
Where?
dxn.
Oh, there's a dxn? Really?
So that's
Cameraman, could you please show us what he's pointing at, or is that too difficult for you? I mean, you have one job.
going to be partial.
The cameraman should come with two cameras, but this is 1,000 years ago. A camera was like $1 million. So I need to 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8. We moved 8 back, and that's the formula that we're dealing with. So it's dxn. Okay, 8. Let's copy it. Let me take it. I'll take it with me so I have it. Okay, I have it. 1, 2, 3, 4, 5, 6, 7, 8.
Of xn with respect to yx.
Okay, so now we're doing dxn. dxn is going to be similar. dxn is partial dxn over partial ys
S
times total dys.
times dys. Now look what I have. I have an expression for ds squared that involves some complicated collection of functions. First of all, m and n are dummy indices. They're summed over. The things which really this depends on are r and s.
Really? But R and S don't show up in the question. R and S, aren't you running over R and S?
The right-hand side doesn't depend on m and n. They're summed over, but it does depend on r and s. So let's.
So ds squared is something summed over, and then dys, dyr. But this s has nothing to do with this s. These are different s's. But this s is a dummy, or I don't know what you mean. I mean, the s and the r are still dummy.
Let's give this a name. This quantity, this whole quantity here.
What is that? That's the partial of this x over this y, the partial of this x over this y. But it's only interesting when it's the same m and n. So only for x is in the same direction. For this x, I don't know. I can't.
It has a value for each r and each s, but it's summed over in m and n. I'm going to give it the name GRS.
Oh, okay. So this is already we're going to end up with this thing in the final equation.
Notice that it has lower indices below.
So this is literally GR. Okay.
Below the fraction bar here. GRS. It's a function of position in general.
Just GRX, okay.
Let's call it of y. Doesn't matter whether we call it as a function of x or y, since if we know something as a function of x, we automatically know it as a function of y. But I want to be working in y notation. So I call this GRS of y, and in general, it depends on y. It's not just a collection of numbers, these are a collection of functions.
Let me see. Oh, only 2 people watching. I'm one of them, so only one person is watching. Maybe not even that.
GRS of y times dy
S
s
D.
dyr.
That's the
Right?
square.
What's the lesson? Oh, of course, this is a special case, or this is similar. It also contains dx's times dx's, but it contains the Kronecker delta. Here we have a very similar thing, except instead of the Kronecker delta, we have a collection of, again, d squared coefficients. For each r and each s, there's a g. It's no longer true that the G11s are equal to 1 and the G22s are equal to 1. They're not. They're all whatever they are.
Mhm.
Nor is it true that G12 is equal to 0.
Mm-hmm.
This is called the metric tensor.
Mm-hmm.
This is the metric tensor. And it's a thing with 2 lower indices, 2 covariant indices, and it's actually easy to prove. It's quite easy to prove that it transforms. In fact, I'll prove it in a moment now.
Oh my God.
It's easy to prove that it actually transforms as a covariant tensor.
I don't know what that means.
How can we do that? I started in this case here with something I knew very well. It's just Pythagoras' theorem in Cartesian coordinates. That led me to introduce, let's call it now, the metric tensor in Cartesian coordinates. This is the metric tensor in Cartesian coordinates. I just read it off from Pythagoras' theorem. And then I changed coordinates to another set of coordinates and found out that the only thing that happens is the delta mn is replaced by a g, which depends in general on position. Okay. Incidentally, for this case, where I started with the blackboard, flat blackboard, when I say blackboard, when I started with a flat space, we know, although it might not be obvious from this form, I might give you some form like this, whether it's obvious or not, we know that we can always transform it back to this form that looks like Cartesian coordinates. We'll come back to that in a minute. But what about the general transformation properties of this thing which I'm calling a covariant tensor? How can we work them out? Well, here's the way. Let's start with a general expression among the x components. Let's not assume that the space that we're talking about is either flat or that the coordinates are Cartesian. All right? That means that we should start with a more general expression here, in which this is Gmn of x. In other words, we should make it look more or less like it looks on this side over here in our starting form. Let's suppose we did that.
Oh my God.
Then
Camera man, come on,
ds squared
faster.
would be given by this general form over here, but
Oh my God, he keeps walking back and forth. We keep missing him.
on this side, we would just replace the delta mn by Gmn of x. What have I shown? I've shown that the GRS in y notation, the y components, are given by the x components times the standard dx by dy coefficients. This is exactly the transformation property of a covariant tensor of rank 2. So the metric tensor is a covariant tensor of rank 2. If I give you a general space, I mean it could be curved, it could have geometric properties which are not the geometric properties of a flat plane. It could be the surface of a sphere, surface of a saddle. We can always write the metric tensor, or the distance between neighboring points, can always be written in this form. The question is, under what circumstances can we find a coordinate transformation from y to x so that this can be brought back to the form delta mn. In other words, is there some, if I were to have given you the y coordinates, and I would have given you the description of the distance between every neighboring point in this form here, that's equivalent to telling you what the geometry is like, if you know the distance between every pair of neighboring points. If I were to give you GRS of y, and I gave you this general form, I can ask the question, is there some does there exist a coordinate transformation which will bring it back to this form which looks like Cartesian coordinates and flat blackboard in 2 dimensions or in 3 dimensions? If the answer is yes, in other words, that this complicated GRS of y can be undone by coordinate transformation and brought to the form of Cartesian coordinates in flat space, then the space is called flat. It means that you may have chosen complicated curvilinear coordinates, but there's no obstruction to straightening out those coordinates and writing it in the form of flat space. That's the definition of a flat space, a flat Riemannian space. The term is Riemannian, refers to this kind of geometry, that there exists a coordinate transformation that will flatten out the metric and turn it just into this collection of zeros and ones. In other words, that it will restore the standard flat space form of the relationship between points, neighboring points. If not, that means there is no way, there is no coordinate transformation which will undo and get rid of the spatial variation, the complexity of this, the fact that this varies from space to space and so on, that point, will not bring you back to this, cannot get back to that. The space is called curved. Curvature in that sense is an obstruction to removing the curvilinearity of the coordinates, if you like. Or in that sense, yeah.
Just making sure I think I understand. Clarify my understanding. If you have a coordinate system that's not Cartesian,
Right.
but you can convert it into this contour delta.
Then it's flat. Right.
I don't know what's going on.
That's right. If you can't, then it's called curved. Now, it's possible that a space be flat in some spaces, in some places, and not in others. For example, this tabletop could be connected to something over here, which was a spherical dome or something. In that case, what is true is over some region of space, you can find a coordinate transformation which will straighten out the metric, but not everywhere. So, you know, a space can be locally flat, so it can be flat in some region, but that doesn't mean it's flat.
It can always be flattened at any one point.
Oh, it can always be flattened in a vicinity, in a differential, infinitesimally small vicinity of a point. Yes, that's right.
What is he
But
talking about?
that, of course, is true. But I mean, sometimes it can happen that the space might even be flat over some extended region. For example, just take this table, put a lump in it, a bump in it over here, and the lump comes up and goes over like that. It has some regions of negative curvature and positive curvature, and those curvatures cannot be gotten rid of. But still, over here, you could still fix up the metric so that it looks flat. All right, that's the basic idea of a metric tensor, and it is the key thing, the key object of Riemannian geometry. The subject we're doing is Riemannian geometry. Yeah.
Can you have a space that's flat except for one point?
Yes, you can. Yes, that's right. The tip of a cone, that's right. A cone is a space which cannot be flattened, but you can flatten out any patch of it. All right, so here's our cone. That's a good point. Here's our cone. And if I slice the cone like that and open it up, I make a thing which looks like this. It can be flattened onto the blackboard. And then if I take my coordinates in the blackboard to be good old Cartesian coordinates, that lays out some coordinates on here, which are flat. But it's always going to fail at the tip. So yes, so the tip of the cone is an obstruction to finding global flat coordinates. I use the term flat coordinates, which is an abusive terminology. Flat coordinates, I mean coordinates with this property.
Oh my God.
All right, let's
kill
is
ourselves.
this clear? Yeah, okay.
Remind-
Let me just do a couple of examples
What do you mean examples?
of metric tensors of spaces. Just the first example is an example
How is it?
which is really just flat space.
How is this
It's
related?
flat space in curvilinear coordinates. We've talked about it abstractly. Let's do it concretely. A specific example of coordinates that we use all the time, in which the lines of constant coordinate, the coordinate axes, whatever you want to call them, are not straight lines. Polar coordinates. Polar coordinates in 2 dimensions, polar coordinates in any number of dimensions, but in particular, polar coordinates in 2 dimensions are examples of curvilinear coordinates in a flat space-time. Flat space. We have not gotten to space-time. Flat space. All right, let's just do it. We can work this out easily. So here we have x and y. Now I'm talking about 2 dimensions, but in these formulas, there's nothing specifically 2-dimensional about it. You may not be able to visualize a higher dimensional curved space. I can't. But you can push the symbols around, and it doesn't really matter whether m and n go from 1 to 2 or whether they go from 1 to 10. You do exactly the same manipulations. But now I am dealing with a 2-dimensional space that you can visualize. So there's x and y, and I'm going to replace them by the polar coordinates, r meaning radial distance, and theta meaning angle. So here's a point, and it's at a distance r from the origin at an angle theta. What we need to know is the relationship between x and y, well, x and r and theta, and y and r and theta. All right, now that's easy. You just drop a perpendicular here, and x, the x location of this point, is equal to
The x location of this point, given r and theta, x of that point, the x is r cosine theta. It's the cosine, isn't it? It's the cosine? Yeah, when they're both, I think it's a cosine. It's r cosine theta. That's the x.
r times cosine of theta, and y
Y is equal to the r sine theta.
is equal to r times sine of theta.
My God, it's been a zillion years since I last saw this.
Cosine of theta is
He has to think about it just like I do. Oh my God, I thought only I have to think about it.
adjacent over hypotenuse, and sine of theta is opposite over hypotenuse, and that's what these things say. Now, I want to write the metric, which we know what it is.
Cosine is the opposite over hypotenuse. So if we multiply by r, we just get the opposite, or the bottom over the hypotenuse. So cosine is the bottom over the hypotenuse. So if you multiply by the hypotenuse, you get the base. Sine is the height over the hypotenuse. So if you multiply by the hypotenuse, you get the height. Okay.
It's just dx squared. Let's write it over here. It's
What
dx
are we
squared
doing?
plus dy squared.
What are we doing?
Over here. It's
The length of
the metric, which we know what it is. It's just dx squared. Let's write it over here.
What do you
It's
mean
dx
the
squared
metric?
plus dy squared. Oh, incidentally, my use of x and y here is not for 2 different coordinate systems now. I should probably
Oh my God, yeah, that's obvious.
call it x1 and x2 to be consistent. But
It's too late.
when I'm dealing with a 2-dimensional blackboard, sometimes I will just call it x and y, and forget this over here. the x squared plus the y squared, which really I should call the x1 squared plus the x2 squared.
Really? Okay.
The x squared plus the y squared is equal to ds squared, right? That's good old Pythagoras.
Yep.
But now all we have to do in order to rewrite the metric in terms of r and theta is to express dx and dy in terms of dr and d theta. So let's do that. Let's differentiate this.
So he's going to do dx
dx is equal
in terms of what? So you have two variables, r and theta. So you need to deal with both of them simultaneously. There has to be a dr component and a d theta component, no?
to the partial derivative of this with respect to r, that's cosine theta, times dr, partial of x with respect.
Oh my God, he should write it out what he just did. So dx is equal to, what is he doing? Cosine theta dr?
To r times dr, plus partial of x with respect to theta. What's the partial of x with respect to theta?
How does x change when theta changes? Oh my, I don't know.
Yeah.
I don't know. Like theta change, when theta changes, how does x change when theta changes? When theta changes, it's cosine. Well, if it's d theta, then it's cosine d theta times r. It's just r cosine d theta.
It's minus r times sine theta, right?
Okay.
When I differentiate cosine, I get minus the sine.
Differentiate with respect to what? The rate of change of what?
So that's minus r times sine theta. Okay, that's the x. And what about the y?
It's the opposite. dy is equal to r sine theta. So it's sine theta dr.
Sorry, times d theta.
Hmm.
And what about
No one noticed. So no one is following.
dy? Same kind of thing. The only
It's cosine theta dr.
difference is now,
Sorry, sine theta dr.
well, this piece is similar. Dr, sorry.
No,
Sine of theta,
dr
dr,
plus r cosine theta d theta.
now it's plus r cosine theta d theta.
But what are you doing? What? Can you explain why? I mean, can you please explain it? Well, why don't you explain it? You didn't write out the rule. Oh my God. It's basically the chain rule, right? So you're modifying r and theta simultaneously. So there has to be a dr component and a d theta component. So the question is, what is dx in terms of the modification when r and theta are changing simultaneously? So dr and d theta. So how does x change? So cosine theta dr, that's fine. This is just a chain rule. Times r, or minus r sine theta. Okay, it's fine.
And now I just want to write dx squared plus dy squared.
Okay, so dx squared plus dy squared, that's fine. So just do summation right beneath.
That's a whole bunch of terms, but they're not very complicated. Let's see
You can see that some of them are going to cancel out and stuff, maybe.
what we have. When I square dx squared, I'm going to get things
Oh my God, you have to square it first. Oh my God, I'm gonna lose my mind. There's so much work here.
involving dr squared. I'm going to
Oh, dr squared and d theta squared drop out.
get things involving d theta squared, and I'm going to get things involving dr times d theta.
Those also drop out. So all you care for is just the dr and the d theta.
All right. Let's look at the dr
Usually that's the way we deal with it because the second order we don't care about.
squared terms. You get one from here, cosine squared times dr squared, and you get one from here, which is sine squared dr squared. When I add them up,
Yeah, but everything is going to be like that, so we cannot deal with it. We cannot drop anything out.
cosine squared plus sine squared is 1. And so I'm first of all going to get that this is equal to the first
Cosine squared dr and sine squared dr is just 1 dr squared.
contribution will just be dr squared.
Hmm.
That's easy.
That's easy. Then at the end, let's see
And
what
it's just gotten by squaring this term and squaring this term and adding them together.
that's good.
Then there's going to be another term which comes with d theta squared.
Okay.
It'll also have
Also, sine squared, cosine squared, and r squared. So it's just r squared d theta squared.
this
But it's plus and minus. So it's minus r squared d theta squared.
squared plus this squared. So it's going to have r squared sine squared theta, and it's going to have r squared cosine squared theta. The minus sign will go away when you square, so it's just going to be r squared
Oh, the minus sign goes away. Okay.
theta squared. The sine squared plus the cosine squared again add to 1.
So it's plus r squared d theta squared.
Is plus r squared d theta squared.
Squared.
And what about the cross term?
Okay, what about the cross? So it's cosine, cosine, sine, sine. So it's again cosine squared, sine squared.
The dr d theta term. Let's look at it. From here, squaring this,
Oh, you're squaring the first line? No, you're multiplying. You're not squaring. You just multiply this by that. So cosine times sine, negative cosine sine, dr, d theta, negative r.
you'll get a cosine theta, sine theta, r with a minus sign. Get r
Okay. Oh, and the bottom is going to be the same. They just drop out. That's good.
cosine theta, sine theta with a minus sign. From this cross term, you'll get plus
Same
r
thing.
cosine theta, sine
They just
theta,
drop out.
and there will be no cross term. All right, so this is the metric of flat space in polar coordinates. Let's write down the components of the metric. The components of the metric are not now just zeros and ones.
Oh my God, 7 more minutes to go. We have to kill ourselves.
The coefficient here is 1, but the coefficient here is more complicated. It depends on position, depends on radius. So, first of all, what's GRR? I use the index R here to represent the R coordinate. I'll use GRR and G theta theta instead of G1 and G2, instead of 1 and 2. What's GRR? 1. Why is it 1? It's just the coefficient of the R squared.
Why is
What about GR theta?
what just happened? Oh, I can press the space bar and it runs fast.
That's the thing which will multiply dr times d theta. Okay? And that's 0. There is none. So that's 0. So far, it looks exactly the same as flat space, but the new thing
I don't know what's going on. I don't know what this G is all about.
comes when I write g theta theta. And that's not 1, it's r squared. So that's the metric of space-time.
What do you mean G? What is this G? I don't know what this metric is. I don't know.
Sorry, I keep saying space-time. That's the metric of two-dimensional flat space in polar coordinates. Now, if somebody gave you this metric and you looked at it, you say, oh, this is kind of complicated. The g theta theta term varies with distance. Is this flat space or isn't it flat space? Can I find a coordinate transformation which will straighten it out so it just becomes dx squared plus dy squared? Well, in this case, of course, we know the answer is yes. And it's just this coordinate transformation. If I gave you this metric, these set of components, and I undid, in other words, I go in the opposite direction and work out the metric in terms of x and y, I find that it's dx squared plus dy squared. So that is a flat space by definition. There are a set of coordinates. There is a set of coordinates. More than one. Of course, you can tilt the coordinates and rotate them and translate them and do all kinds of things. But there's at least one coordinate system where the metric just looks like the Kronecker delta. So that's flat, despite the fact that in this form, things have a nonlinear complicated dependence on the radial distance.
Right? Yeah. Does the off diagonal term being 0 tell you anything about the space?
Yes, it doesn't tell you anything about the space in this case. It tells you something about the choice of coordinates. I'll tell you, no, good, I meant to come to that right now. Let me tell you exactly what it tells you. It tells you, let's look at the lines of constant r and the lines of constant theta. The lines of constant r are circles. The lines of constant theta are straight lines from the origin. The fact that there's no cross
Jesus
term
Christ,
is
you can't see anything he's drawing. My God.
an indication that the lines of constant r and the lines of constant theta are perpendicular to each other.
Constant R are just circles, constant theta are just lines, okay?
That's also, of course, true for the lines of constant x and y. They're perpendicular to each other.
Interesting. So they're perpendicular to each other in every transformation, okay?
But that's the meaning of the cross term vanishing, that the r and theta, or that the axes, the lines of constant coordinates, so you can think of them as the axes, are perpendicular to each other. That I have not changed by doing polar coordinates. I could have used some more complicated coordinates, for example, ones which look like this. That's an interesting exercise. Find some coordinates which have some, where these lines are not perpendicular, and then you would have had a gr theta. Okay, so there was nothing particularly special about the fact that this vanished, other than my particular choice of metric happened to have this perpendicularity aspect to it. All right, let me give you the metric for a sphere, and I will allow you to prove that you cannot straighten out the sphere, that you cannot find coordinates in which the sphere is flat. This is a unit sphere of radius 1. That doesn't matter very much. That's got nothing to do with it. I've just chosen the sphere to have radius 1. All right, so here are my coordinates. Now, I could use many different sets of coordinates on the sphere. It doesn't matter which set of coordinates I use. I won't be able to straighten out the coordinate system, but I'm going to give you one set. And the one set is basically good old longitude and latitude, except I always measure longitude from the South Pole. In other words, no, I measure latitude from the latitude from the South Pole, right? Longitude, and then it goes east-west, right? This is another thing I can never remember. Longitude is east-west, latitude is north-south, and just because I'm used to it, I always choose the latitude, yes, the latitude to be 0 at the South Pole.
Mm-hmm.
All right, so you pick a point on the sphere.
Sphere is something like x squared plus y squared plus z squared equals 1. I think that would be the definition of a sphere. Although I don't think you can, a sphere is not a function in Cartesian coordinates.
Doesn't have to be on the great circle, and you locate it by a polar angle. The polar angle
So it's theta phi r.
is one word for it, or latitude, which I'll call phi, and also a longitude, which I'll call theta.
Theta.
Those are two coordinates good set of coordinates for a sphere. The lines of constant theta and the lines of constant phi are perpendicular, so I still have a case where I'm not going to have a cross term. And now you can take any small vector or any small interval. The small interval is characterized by a d theta and a d phi, and you can write down the distance from one point to another using Pythagoras' theorem on the sphere, and I'll write down the answer for you. It's just d phi squared. As I said, this is radius r equal 1.
So r is equal to 1. So d phi, I don't know.
It's d phi squared plus sine of theta, sine of phi squared, sine of phi squared, d theta squared.
My God. That's the end of that. Oh my God, it's the end of the lecture. They ended it before he ended it. My God, I don't know. I mean, this lecture was terrible. Absolutely. Yeah, absolutely terrible. Absolutely terrible. But what is the Riemann zeta function? Bell's theorem. Time is but a stubborn illusion. I'm trying to think. I want to see what 5 looks like, but I really need to review this. I really need to go over this. This is basically nonsense. I understood most of it until he got to the covariant and the contravariant. Distinguish the difference between them and the definition of each one and up and down. From that point, I was lost. Until that point, I was able to follow nominally. What's this? So there's another guy who teaches all of GR in 2 hours. We could try and watch him and see if he explains it better. Ta-di-da-lee-la-la-la-la. Uh, uh, uh. Anyway, we're gonna stop here. I'm gonna take a break. Oh, Nick, he is too advanced for me. It's not about being advanced. I went too fast. I should have slowed down. But I think I'm gonna watch somebody else go through GR first. I'll maybe we should watch someone else who does it in a simpler way, less deep way. And then we'll come back to this one maybe. Anyway, I'm going to stop here. We'll see you next time. Bye.